Hello everyone and welcome to this next lecture in the DC to DC converter series. So in the previous lecture we had completed the ZETA converter, that is this one, and this is the circuit of the ZETA converter. So we had simulated the ZETA converter, we had simulated with the fixed duty ratio, we had also simulated in the open loop control mode where we had varied the duty ratio from 0 up till around 0.8 in small steps to actually see the output. So these are the outputs, as you can see, as the duty ratio increases. So this is, for example, number 1. This is the capacitor voltage and this is the output voltage. So as you can see, the output voltage increases from 0 until a fixed amount where the duty ratio remains constant, and this is when the duty ratio is 0.8, and we had verified the operation of the ZETA converter. So now with this we are done with the basic non-isolated DC to DC converter series. Before I continue with the flyback, or rather something which like the isolated converter series, such as the flyback or the forward, I thought I would do a little bit of a discussion on the 3 latest converters that I did, that is the CUK, the CUK and the ZETA. So as before I start this lecture, a little bit of background, that if you are interested in these kind of video lecture series but you would like something a little more comprehensive, I do have full-length online courses on the MOOC website Udemy. So this is my latest course, Simulation of Magnetics for Power Electronics using Python. In this course, I talk about how you can use Python to simulate transformers. So I cover a little bit of basic theory about magnetism and magnetic circuits. I simulate transformers, I simulate a multi-winding transformer, and finally there is a case study of a flyback converter with a high frequency transfer. If you are interested more on the digital signal processing and control side, I do have another course, Basics of Digital Signal Processing for Power Engineers. In this, I deal with how you can design filters for power applications. So I discuss a little bit of basic theory of signal processing, and we simulate, or rather design, several filters, which is a low pass filter and a notch filter, using frequency response characteristics in Python programming, and we implement and simulate them. I mean, we don't implement them in hardware, we simulate them in Python again. And finally, the oldest course, which is simulating power electronic circuits using Python. In this course, I talk about the basics of how you can use Python for simulating power electronic circuits. So there's again a little bit of basic theory about power electronics. There is a background on Python power electronics, how to install it, how to use it, and there is eventually a case study of simulating a buck converter. So if you are interested in full-length online courses, the links to these courses are provided in the video, so please do check them out. So with this, let me continue. So let's go back to the circuit. So this is the circuit of the ZETA converter, right? Let me open the circuit of the CUK converter as well. And let me open the second converter. So the CUK converter, as we were drawing the different converters, we saw that there was a fair degree of similarity between them, right? So let's compare the CUK converter with the ZETA. And for this, let me resize this. And let me resize this as well, so that I can place them side by side. So I have the CUK on one side, I have ZETA on the other. So the first and foremost difference is, in the case of a CUK converter, the input voltage is directly connected to some part of the circuit, right? You see the switch is in the parallel path, right? This follows the construction of the boost followed by a buck. Whereas in the case of a ZETA converter, you see that the switch is in the forward path, right? So which means the switch will bring the rest of the circuit in connection with the input, or will disconnect it from the input, right? So this ZETA is more like a buck followed by a boost. Now let's keep going. We see here that besides this, there is in both cases a decoupling capacitor, right? But the role played by the decoupling capacitor is very different, right? Now, in the case of a CUK and the ZETA, the diode, however, is in this parallel path just after the capacitor. But in the case of a CUK converter and the case of a ZETA converter, the polarity of the diode is very different, right? In the case of a CUK converter, the diode polarity is pointing downwards because the current through the diode will flow downwards in this branch. In the case of a ZETA converter, the current in this diode will flow upwards, right? So let's look at this in a little more detail. And the rest is pretty much the same. You have the inductor and you have the capacitor. So let's look at the operation. In the case of a CUK converter, when we turn on the switch, the voltage source charges the inductor through the switch. And since this switch is the low resistance path, the current will flow through the switch and the source will not supply any current to the rest of the circuit. So the capacitor and everything after the switch is disconnected, right? In the case of a ZETA converter, when the switch is turned on, the rest of the circuit gets energized, which means the inductor and the capacitor, right? So there is no isolation in the case of a ZETA converter as there is in CUK converter. In the CUK converter, when the switch is turned on, the rest of the circuit is isolated. In the case of a ZETA converter, when the switch is turned on, the entire circuit gets connected, right? Which means there is a parallel path. The inductor gets charged and the capacitor gets charged. So at the same time, when the switch is turned on, this capacitor will discharge through the switch, right? And along with discharging through the switch, this capacitor will charge the output capacitor through this inductor, right? So the inductor and the output capacitor are being charged by the capacitor, this decoupling capacitor, right? Now the diode does not conduct. Remember, the diode does not conduct because the current through the diode has to flow downwards, and the current through the diode, and since in this case the current is trying to flow upwards, because remember the capacitor is discharging in the counterclockwise direction, which means the current will have to flow upwards, which is not possible, right? This diode conducts downwards. So in this case, if the inductor is charging and the output capacitor is being fed from this decoupling capacitor. In the case of a ZETA converter, when the switch is turned on, the capacitor is being charged by the input voltage, right? Here the capacitor was discharging. Here the capacitor is being charged. The inductor is charged, the capacitor is charged. And along with the capacitor being charged, this inductor also is in the forward path, that is also being charged. So in the case of a CUK and the ZETA, one thing is common. Both inductors are charged at the same time, right? Both of them. Here, inductor L1 is charged by the input voltage. Inductor L2 is charged by the capacitor, decoupling capacitor, C1. Here, in the case of a ZETA converter, the input inductor L1 is being charged by the voltage source, and inductor L2 is also being charged by the input voltage source. Okay. This is common between the CUK and the ZETA. Now, when the switch is turned off here, now the voltage source will now charge this capacitor through the diode, because the diode is the polarity of the diode is downwards. So therefore the diode will form a low resistance path for the current that is charging this capacitor. So the input voltage charges the capacitor through the diode, through the freewheeling diode. Okay. And here, when the switch is turned off, this capacitor, which was being charged by the input voltage, now discharges and freewheels through the diode. In this case, the current flows upwards, right? And at the same time, here in the case of a CUK converter, the diode, which is now being charged by the input, or rather the capacitor is being charged by the input voltage. Along with that, the inductor freewheels through the diode and provides power and supplies power to the output capacitor. And here also the inductor charges, or rather the inductor doesn't charge. Inductor freewheels through the diode and supplies the output capacitor. In this case, the current flows towards the right, because current in the inductor was flowing towards the right. It will continue to flow towards the right and it will supply the output capacitor in the clockwise direction. Here it is in the anti-clockwise direction. So the huge difference between the CUK and the ZETA was that the voltage of the output in the case of a CUK is the reverse of the input. Here the voltage of the output is the same as the input. Right? This is a huge benefit of any converter, because now you can ground one terminal of the converter. So with this little discussion, what we can do, the main question here, the biggest difference is the size of the capacitor and the current flowing through this capacitor. In the case of a CUK converter, it is this capacitor which is connecting two parts of the circuit. Right? The capacitor receives current from the input voltage source and it supplies power to the output voltage. Right? Here in the case of a ZETA, the capacitor is not connecting two parts of the circuit. Both parts of the circuit are being connected. When the switch is turned on, the output is connected to the input. Right? So the capacitor doesn't play a connective role. The capacitor is merely an energy buffer. In this case, the capacitor needs to be much larger and the current is going to be much different as compared to the current here. And that is what we are going to examine. So let's run over to our simulation. And let me go over to the simulation library and let me open this in a new tab. And let me open the CUK converter. Okay, I need to process the circuit schematic. Oh, the circuit schematic should not be right. Let me just, there's an error in the simulation parameters. Yeah, because I think this has changed. The directory has changed. Let me go over to the CUK converter and let me edit the directory, the working directory. So this is when I first created it. I probably moved it. And now it should be, yeah, now it's being read. So we should be okay. Yeah. So the first thing I'm going to do is I'm going to go and change something, because we have included the open loop control in both our simulations. Let me open the gate signal.py and here too the gate signal.py. So let me remove this open loop control and bring in a constant modulation signal. So let me just put it 0.5 to be exactly halfway. Actually, let me make it 0.6 so that it's in the boost mode. Let's bring it here and put it 0.6. Right. So let us run these two simulations. So this is the ZETA converter and this is the CUK converter. Actually, this is the ZETA and this is the CUK. So let me run this ZETA and let me run the CUK as well. So there are no errors, it's okay, and it is acceptable to run simulations in parallel. So this is not illegal. You can run simulations in parallel as long as the working directory is different, because remember, the circuit output.dat file is being written by the simulation. So if two simulations are writing the same file, your results are being overwritten. So make sure that your simulations, when they are being run in parallel, are in different directories. So let us check out the capacitor voltage and the capacitor current. So we have the capacitor voltage. Let's plot this for the ZETA. And let's plot it for the CUK. This is the decoupling capacitor voltage. So in the CUK converter, this is the decoupling capacitor voltage. And for the CEPIC, this is the capacitor voltage. So let's put these two together. So, as it is quite obvious, for the same ratings, the CUK converter has a much larger capacitor voltage, right? So now the question is, what exactly is happening? Actually, I'm in the wrong simulation. ZETA converter. Actually, close this. We have the ZETA converter. This is the capacitor voltage. Let me close the other one down. Yeah, because it should be negative. Let me just close this one down. And let me open the other one as well. Yeah. Alright, so let's place these two together and compare them. So in the case of a CUK converter, the voltage is positive. In the case of a ZETA converter, the voltage is negative. Right? And we've seen this in the simulations as well. The reason is simple. Come back to the circuits. In the case of a CUK converter, when the switch is turned off, the input voltage charges the capacitor. Right? So this is the reason why the voltage across the capacitor is positive with a polarity towards the left. Now, in the case of a ZETA converter, when the switch is turned on, the capacitor is being charged by the input voltage, but when the switch is turned on, the capacitor discharges through this diode, right? So now the question is, what is the voltage of the capacitor and who controls the voltage of the capacitor? Now, we've already seen this in the previous lecture, that when the switch is turned on, right in the beginning, the entire voltage drop appears across the input. So therefore, this capacitor voltage balances out the output voltage, right? It balances out the output voltage. In the case of a CUK converter, however, that's not the case. Why? Because in the case of a CUK converter, it is the capacitor which balances out again the output voltage, but in this case the output voltage is negative. So let's go back and have a look. If we compare in the two cases, the voltage across this CUK converter is almost double the voltage across the ZETA converter. Now, if we examine what exactly is happening, in the case of a CUK converter, let's say for example, we apply our KVL loop. We have the voltage source, we have an inductor, we have the capacitor, and we have another inductor and we have a capacitor, right? Therefore, the voltages will add up across these, right? The voltages, that is, applying KVL, the loop voltage will be 0. So therefore, this decoupling capacitor has a voltage that is equal to the sum of the input voltage and the sum of the output voltage. Let's verify this. So, in the case of a CUK converter, let's plot the output voltage. This is the output voltage. Yeah, see, this is the output voltage. And you see the output voltage is somewhere at 18 volts, minus 18 volts. Now, if you look at minus 18 volts, the input is 12 volts. It is the sum of these two, that is the absolute sum, taking 12 plus 18. That is what you see here in the CUK converter. That is, the voltage of the decoupling capacitor of the CUK converter is the sum of the input voltage and the output voltage, neglecting the sign. Right? The result is this decoupling capacitor has to withstand a bigger voltage than both the input and the output. Right? This is a significant stress on the decoupling capacitor. As opposed to that, in the ZETA converter, this decoupling capacitor only withstands a voltage equal to the negative of the output voltage. Right? This voltage is merely the negative of the output voltage, which we saw was 18 volts. Right? So, this is a comparison of the decoupling capacitor in the CUK converter and a ZETA converter. Right? That the voltage across the decoupling capacitor of the CUK converter is much larger than the voltage across the decoupling capacitor of the ZETA converter. The reason the decoupling capacitor in a CUK converter connects two parts of the circuit. In a ZETA converter, the decoupling capacitor does not connect. The two parts of the circuit, that is the input and the output, are already connected together. That is the major difference. Right? So now, there are a few other differences which we will examine. However, this lecture is getting a bit long. So, I would like to end this lecture here. So, the next lecture, we will look at the current in these capacitors and also try to look at the current, or also try to do a comparison between the ZETA and the CUK and the CUK. This was just between the ZETA and the CUK. We will also compare the ZETA and the CUK. Right? I mean, there is no converter which is absolutely the best. You have to choose what it is you want. But this comparison is interesting because their topologies are very similar. So, as before, if you have any doubts, please do post in the comments or write me an email or message me on social media, whichever is your preference. Otherwise, I will see you in the next week where we will continue with this comparative analysis. So, thank you so much for watching and see you next time. Goodbye for now.